Most of this information in the video has been taken directly from your Caboodle textbook. What I will do is to walk you through the information in the textbook, walk you through a few exam questions and get you to practice. So, the learning objectives for this unit, as stated here, are to describe how the absorption or infrared radiation can be used to indicate the presence of certain functional groups. So that means, as well as your test tube reactions, you need to be able to use this analytical technique to identify the presence of certain functional groups in your organic molecules. Also, you're going to be asked to explain what the fingerprint region is and how it can be used to identify the identity of a compound. And also, you've got to be able to explain how an infrared spectrum can be used to show the presence of impurities in your organic molecules. This is purely a revision resource, so I'm not going to go into the technical details about how an infrared spectrum is derived, only to say that when organic molecules absorb infrared radiation, their covalent bonds are caused to stretch or bend, and this results of light or infrared radiation being taken out from the spectrum, which we see here as these peaks. So a typical infrared spectrum looks like this. Notice that on the x-axis here we've got wave number which goes backwards, and on the y-axis here we've got something called transmittance. So the more infrared radiation that is absorbed, we get these so-called peaks. They're really troughs where infrared radiation is taken out by covalent bonds absorbing the radiation, and as I said, causing the bonds to stretch or bend. So these bonds are stretching and bending because of the infrared radiation being absorbed. Remember, a covalent bond is a shared pair of electrons, and as they absorb infrared radiation, the bond can stretch, it can bend, it can scissor. Data that correspond to the frequencies of the different bonds will be given to you in the exam on the back of the periodic table. So these three figures here, figure 4, figure 5 and figure 6, all refer to the infrared spectra of ethanol, ethanol and ethanoic acid. And I'm going to walk you through the key peaks that have been marked here. Both ethanol and ethanoic acid possess a carbonyl group, a C-double bond O. And you will notice that both ethanol and ethanoic acid have a sharp peak, sharp as opposed to what we call a broad peak, a wide peak here. And we can see the corresponding infrared absorption data, so you will find this on the back of your periodic table. For a carbonyl compound, the carbonyl group absorbs infrared radiation between 1680 to 1750 centimeters to -1. That is called the wave number. So both of them have a sharp peak between 1680 and 1750. As soon as you see this peak, you can see here, you know there is a carbonyl compound. You know there is a carbonyl group in your organic molecule. If we go to ethanol, there is no carbonyl group, and hence there is an absence of a sharp peak at 1680 to 1750. So how do we distinguish the aldehyde from the carboxylic acid? Well, the carboxylic acid, as well as having a carbonyl group, also has a hydroxy group on the same carbon. Ethanol doesn't. And you go to your data sheet and you can see that in carboxylic acids there should be a broad peak at 2500, range of 2500 to 3000 centimeters to the -1. We go to our spectrum and we can see clearly here that this peak starts at about 2500 and ends at about, you can see here, about 3000. So this broad peak here tells you that there is a hydroxy group present in a carboxylic acid. Now, if we go to our alcohol here, ethanol also has a hydroxyl group. But the absorption of OH group, or the hydroxyl group in alcohols, as you can see here, is at a different position than in carboxylic acids. So whilst they're both giving a broad peak, the alcohols doesn't start to absorb till 3230, so it's further along in this direction. So the absorption starts much later at 3200, and that's how you can distinguish between the OH group in alcohols and the OH group in carboxylic acids. Notice also that carboxylic acids have a carbon-oxygen bond and alcohols possess a carbon-oxygen bond. And you can see here the carbon-oxygen bond here absorbs at 1000 to 1300 centimeters to the minus 1 in both carboxylic acids and alcohols. So the thing to distinguish an alcohol with a carboxylic acid is the absence of this sharp peak here of the carbonyl group. How do you distinguish between an aldehyde and a carboxylic acid? The aldehyde does not have a broad OH peak at 2500, whereas the carboxylic acid does. These two infrared spectra have been taken from Doc Brown's website. So let's have a look at what we mean by the fingerprint region. Well, it says here that the area of the spectrum below 1500 centimeters to minus 1, this is this part here, is caused in part by very complex vibrations of the whole molecule. And it's really unique for any particular substance, just like your fingerprint is. And therefore, it's called the fingerprint region. So let's take an example. These two compounds, propanal and propanone, have the same molecular formula but different structures. They are in fact functional group isomers. So you can see here, this propanal is an aldehyde, C double bond O H, and propanone, its functional group isomer, is a ketone. The carbonyl group is in different positions. So you couldn't use the functional group to determine which molecule was which, because they both have stretching between 1740 to 1720, which is caused by the presence of the carbonyl group. So they both have an identical functional group, which is a carbonyl compound. You can see there's some slight difference here, but these are just stretching of CH bonds that most hydrocarbons have. But if we go to this part of the spectrum here, below 1500, which we call the fingerprint region, you can see they're both completely different. And this fingerprint region is how we would be able to identify the difference between these two functional group isomers that both possess the carbonyl group. The data of every single organic compound can be stored, and therefore the fingerprint region can be used and identified from a database of compounds. So you've got an exact match, you know it's that compound, just like fingerprints. A question that always comes up in multiple choice is which of these gases is not a greenhouse gas? And the odd one out is nitrogen. And we know this because there is about 78% of nitrogen in the atmosphere, and if it was a greenhouse gas, we'd be absolutely boiling. Now, what you've got to take into account when you talk about greenhouse gases is what we call the relative greenhouse effect per molecule. So if we look at a molecule of dichloro-difluoromethane, so that is a molecule of methane with the hydrogens replaced with two fluorines, difluoro-dichloromethane, you can see that the relative greenhouse effect per molecule is 25,000 times that of carbon dioxide. So why is carbon dioxide so problematic when it's got such a relatively low greenhouse effect? Well, we need to then look at the concentration in the atmosphere at parts per million. So if we look at the absolute concentration of carbon dioxide compared to this dichloro-difluoromethane, you can see it's significantly higher. Even though it's only 350 parts per million, the concentration of this chlorofluorocarbon is much lower. Another anomaly is water vapour. Water, the OH group, definitely absorbs in the infrared spectrum. If we go back and have a look at the absorption of the OH group, we remember it absorbs around 3,000 centimetres to the -1, depending on the molecule. And we don't include it in the table because depending on where you are in the world, the concentration is very variable. But the higher the concentration of water vapour, the more infrared radiation is being absorbed. So these are some questions from your Caboodle textbook, these summary questions, which you can go on to answer. The answers are at the back. I'm not going to walk through them in here. So you need to be able to remember that it's the relative greenhouse effect per molecule. So even though carbon dioxide is low, its concentration compared to other molecules is very high. And remember also that water, because it contains OH groups which definitely absorb in the infrared, water definitely is an infrared, is a greenhouse gas. I'm now going to walk you through some of these past paper questions that can be found in your Caboodle textbook. These start on page 250. This first question shows you an infrared spectrum and you're given the molecular formula or the organic compound, which is C3H6O2. It's asking you to identify the functional groups and to draw the structures of the 3 possible structural isomers for A. So the first thing you'll need to do is to have your data sheet. Immediately we can identify the peak at Y because we can see that it's absorbing in the region of 1,680, we draw a line down here, to 1,750. So therefore we've identified that as the carbonyl compound. So now what we need to do is to draw structures of the molecule, as many structures as possible, with C3H6O2. Now we can see that it's unsaturated, but that is because of the presence of the carbonyl group, and also we know it's not an alkene because there is no absorption here between 1,620 and 1,680. We can also see that there is another peak here, and if we try to identify this peak, we know it's in the range, so it could be an OH group for alcohols or an OH group for acids. Now the OH peak has a slightly higher wave number than an acid. You can see here an acid starts to absorb about 2,500, and this peak starts to absorb a lot further along, which is about 3,200. So we can iron out the fact that our molecule is a carboxylic acid. So let's now start to draw structures with the carbonyl group and an OH group, because we've already identified and eliminated that it is a carboxylic acid. Can't be an alkene, remember, because we've already said there is no double bond, there is no peak for a double bond. So the possible structures are either an aldehyde or a ketone, and now we need to put the OH groups on. So we could have an OH group here on our aldehyde, could be on position 2, or it could have been on position 1 on the aldehyde. So the OH group could have gone here on position 3. However, if we go to our ketone, the OH group can only ever be on carbon 1 or carbon 1. So the OH group on the ketone could only have been here. So there's only one alcohol isomer of the ketone. The first part of this question simply dealt with different types of isomerism, so I'm going to walk through that quickly just as a bit of revision. So it says complete the table by naming isomer 3. So first of all, we can identify the functional group. We can see it's a ketone, and if we number the positions, starting with the lowest first, that's on carbon 1, 2, 3, 4, 5. It's a ketone. It's got 5 carbons, so the stem is pent, and the carbonyl group is on position 2, so it's pentan 2-one. Notice we follow by a vowel, so we have to put an N in because this is we have to put a consonant N in because we're followed by a vowel O. The structural isomerism, well, they're all different functional groups because this is an alcohol and an alkene. This is an aldehyde and this is a ketone, so that is functional group isomerism. So remember, they're all same structures but different functional groups. So the compound Z-pentan pent-3-ene-2-ol is a stereoisomer of E-pent-3-ene-2-ol. So draw the structure of the Z isomer. Well, all you need to do is to identify your priority groups, and if we use a Kahn-Ingold pre-log, we can see here that that is the priority group because carbon has 6 protons, hydrogen has 1. We go to the other side and we can immediately identify this as the priority group because carbon has 6 protons and hydrogen has 1. So E entgegen enemies, so all you would need to do is to then draw the priority groups on the zusammen side to get the Z isomer. So we simply flipped the priority groups to the same side. So that was a nice, straight and easy question. So identify the feature of the double bond in both of these that causes the compounds to be stereoisomers. And remember, there is restriction of rotation about the bond. Let's now move on to restriction of rotation. So let's now move on to the next part of the question. The next part of the question asks about chemical tests. And if we just look at the functional groups in each of these, we can see that pent-3-ene-2-ol contains a secondary alcohol, and it also contains an alkene, a double bond here. We can see that isomer 3 is a ketone. And we know that there are not many laboratory chemical tests on the AS syllabus to identify ketones. But you certainly know chemical tests to identify an alkene and a secondary alcohol. So there's 2 possible answers here. And probably the most simplest one is if you shake an alkene, anything that contains an alkene with bromine and water, you will notice that it changes from an orange-brown colour to colourless. Make sure you give the start colour and the end colour. So the solution goes from orange-brown to colourless because the bromine adds across the double bond. That was from the previous video. With the isomer 3, there would be no visible change. So let's now look at the question which talks about the infrared spectroscopy. To answer this question, we're going to need our data sheet. Immediately, we can eliminate the fact that it's an aldehyde or a ketone due to the absence of a peak at 1680 to 1750. There is no sharp peak here, which tells us that there is no carbonyl group. We also know that there is an alcohol group present because of this broad peak here between 3230 to 3550. So that broad peak there tells us an OH group in an alcohol. Also, to confirm that it was the first isomer which possessed a C double bond C, there should be a peak at 1620. So if we go along to 1620, which is here, it's a very small peak, so 1680, that tells us that there is an alkene. Notice this bond, this peak is very small, but it is indicative of the presence of an alkene group. And therefore, we have identified that it was in fact isomer 1. Let's remind ourselves of the structure of isomer 1. So the group that's responsible for the OH at 3230 to 3550 is this OH group here. This very small peak here indicates at 1620 to 1680, this very small peak here is due to the alkene group.